Hello everybody, welcome to 7.2, Evaluating Trigonometric Functions. Today we're going to relate trig functions to reference angles and use special right triangles to evaluate trig functions. And then we're going to use reciprocal trigonometric identities and Pythagorean identity to evaluate trig functions as well. Alright, so let's start talking about reference angles. So if you remember from class, we talked about reference angles being the angle formed by the x-axis and then our terminal side. And so in this case, we are going to evaluate theta at 4 different points. And it's really just anywhere in these quadrants, right? And we're going to give them a general value of x and y. And then you'll notice some of them are negative, but that's just based on which quadrant they're in. Okay, so let's just take this first theta, for example, right? You'll notice that this first theta has point x comma y. And we already know that that theta has the values for cosine of x, sine of y, and then their tangent is going to be y over x. This theta here is just this angle. It's going to be 0, right? Because that's what this would be. It's going to be 0 pi plus whatever theta is, and that's going to be our reference angle. Should be pretty intuitive. Like if theta was 20, our reference angle would be 20, because in this quadrant, whatever theta is just what the reference angle is. You're not really doing any math to it. Then when we move here to this blue one, right? Now we're referencing this negative side of our x-axis, right? And our theta is actually created by taking whatever pi would be and subtracting it, right? So our cosine and our sine in this case are actually going to be both pi minus theta, right? Our x is going to be negative, our y is going to be positive, and our tangent therefore would be y over negative x. But remember that it's whatever pi is minus this distance, right? Whatever the distance of theta is. So in other words, this could be, if this reference angle was, this could be 180 minus 20, let's say, something like that, right? And that would of course give us an angle of 160 degrees. But it is minus this theta. All right, now you'll notice that on this orangish yellow color here, now we're in the third quadrant. You'll notice that the x and y values are both negative for cosine and sine. Therefore, tangent is negative y over negative x, which is the same as just positive y over x, right? And in this case, we're going to take pi and we're going to add theta to it, right? Whatever the value of pi is, we would be adding a little bit more. All right, and then finally in this last quadrant, it's kind of the exact same idea. In this case, you'd have 2 pi and you'd be subtracting a little bit. Or you could even go negative, right? Usually we're going to stick to positive angles, in which case, it's going to actually go all the way around, and it's going to actually be 2 pi minus a little bit, right? Or whatever theta is. All right. So let's go and use this to solve problems. Like what is this? How does this help us? So if we're given a cosine value and a sine value, or even an x and a y value, we can use reference angles to refer to other reference angles that are the same reference angle, and we can use it to solve problems. So given that cosine is 75 degrees, or cosine of 75 degrees is 0.26, and sine of 75 degrees is 0.97, we want to find sine, cosine, and tangent of 105 degrees and 285 degrees. So first of all, if we know that the cosine of 75 degrees is 0.26 and the sine of 75 degrees is 0.97, we know that that's a point on our graph, right? Because our cosine relates to our x value, our sine relates to our y value. So we know that, and they're both at 75 degrees, right? So at 75 degrees, our point is going to be 0.26 comma 0.97, right? And this is 75 degrees. So 75 degrees would be our theta from what we were just looking at before. And what that means is if we go 75 degrees from 0, we'll get to our point. If we go 75 degrees backwards from 180, we can get to our point, right? Which is what 105 is in this case. If we did 180 minus 75 degrees, we'd get to 105. So these are the same reference angle, right? Just in different quadrants. And then if we look at 285, right? If we went 360 minus 75 degrees, we would get 285. So all three of these are the same reference angle. So we can use that to solve our problem, right? If we know this is 0.26 and 0.26 and 0.97, all we have to do now is just apply the sign that makes sense for the quadrant. So of course, in our first quadrant, everything's positive, right? At 105, our x value is negative, so it'll be negative 0.26 and positive 97, right? And I can kind of show you here. I did some of the math for you. I've already kind of explained this, right? We took the first one and we subtracted 75 from 180. And then on this 285, we subtracted 75 from 360. And so, yeah, so these share the x and y values. And we just need to determine positive and negative. So for 105, which was in that second quadrant, we're just going to take the negative of x values. So our sine of 105 is 0.97. Our cosine of 105 is negative 0.26. Remember, that's the negative now. And then the tangent, we just put the y value over the x value, and we get negative 3.373. And then in quadrant 4, our y values are negative, but our x's are positive. So we take the same values from before, but this time we have to make the 0.97 a negative. Our cosine is 0.26, and our tangent is just our sine value over our cosine value, which again gives us negative 3.73 because they both have one negative value associated with them, right? So it's going to be the same. All right, so that's it. That's how you can use any reference angle, right? If we know the reference angles and we know the values, we can use that all across the board. And actually, if you want to take some time to look at something interesting, look at the chart I gave you in the last one with all of the different parts of the unit circle. You'll notice that if you evaluate each of the reference angles and then you look at the points associated with them, you'll see that it actually works out really well. And you'll see that a lot of the points are exactly the same. The only difference is that some of them will have negative and positive values based on what quadrant they're in. All right, so next thing, using 30, 60, 90 and 45, 45, 90 triangles to evaluate trig functions. All right, before we jump into this, I'm going to just quickly go over what a 45, 45, 90 and 30, 60, 90 triangle are, and then we'll get into the problems. I know in your notes they're kind of all tied together, but I wanted to go over these a little bit separately first and then jump back into it. So if we look at this little chart here, right, you'll notice that I articulated what a 45, 45, 90 triangle is. So first of all, if we have our right angle down here, I'll try my best to draw this triangle, but if we go across from the 90-degree angle, we have what's known as the hypotenuse. And then each of these 45-degree angles, because it's an isosceles triangle, each of the legs, because they both correspond with a 45-degree angle, are going to be the same measure, right? I've always called the little leg lowercase l, right? So in this case, our legs are L, and our hypotenuse is L times the square root of 2. And you could do that if you wanted to figure out how this is L times the square root of 2, just use Pythagorean theorem, right? L squared plus L squared equals C squared, right? And then when you do the math, you get L times the square root of 2. So that's where this comes from. So, in other words, if I know the leg was 4, I know my hypotenuse is 4 times the square root of 2. And if I know that my hypotenuse is like 6 times the square root of 2, and then I know my leg is 6. And of course, it can get more complicated with radicals and things like that, but that's the general idea of a 45, 45, 90 triangle, all right? So, let's go and jump into the problem with it, and then we'll talk about 30, 60, 90 all at one time. So, find sine of pi over 4 and cosine of pi over 4. Well, one thing you could do if you wanted to find pi over 4 very quickly is say, okay, well, what is pi? Well, pi is 180 degrees, right? If I take 180 degrees and I divide it by 4, I'm going to get 45 degrees. So pi over 4 is 45 degrees. All right. So, yeah, let's go ahead and jump into it knowing that we're talking about 45-degree angle over here, right? And if this is 45, we can generate a right angle here, and which would make this other angle have to be 45 degrees, right? So we're talking about a 45, 45, 90 triangle over here. All right, so we know that in the unit circle, our hypotenuse is going to be 1, because this radius from here to here has to be 1. So we can kind of use that to solve, right? So using 30, 60, 90, and 45, 45, 90 triangles, let's go ahead and find sine and cosine of pi over 4. So first of all, we know that our hypotenuse is our little leg times the square root of 2, right? This is the formula for it. Hypotenuse equals this. So if we know our hypotenuse is 1, we can plug in a 1 for the hypotenuse, right? So this hypotenuse word just becomes a 1. So 1 equals x times the square root of 2, and then we divide both sides by square root of 2, and then we have to rationalize. If you need help with the rationalizing, please let me know. And you're going to get the square root of 2 over 2. So this is the length of one of the little legs, right? So the little legs are each the square root of 2 over 2, and our hypotenuse is just 1, right? So what this means is that our x value, because both of the legs are the same, right? Our x and our y are going to be the same value. So our x value is the square root of 2 over 2, and our y value is the square root of 2 over 2. Which means if x is square root of 2 over 2 and y is the square root of 2 over 2, that means sine of pi over 4 and cosine of pi over 4 are both that same value. All right, not too bad. And remember, if you have reference angles, or if you're using reference angles, right, this is pi over 4 greater than the x-axis. So over here, if you would take pi over 4 away from pi, right, then you would get another 45-degree angle over here, and you could use all of these values. You would just have to take the negative of the x value. All right, so let's go ahead and jump into pi over 6 and pi over 3, which are 30-degree and 60-degree angles. Now remember, you could always take pi, which is 180 degrees, and divide it by this number. So pi over 6 is going to be 30 degrees, and pi over 3 is going to be 60 degrees, right? You can just divide them. Now, let's quickly go into what a 30, 60, 90 triangle is. And this is a little bit more complicated than the 45, 45, 90 triangle, but it's still the same idea. You follow a set of rules, you plug in the information you have into like a mini formula, and you can use that mini formula to solve for things. So in this case, we're going to have more than just hypotenuse and legs, right? Because the legs on this one aren't going to be the same. So we have to differentiate between the length of the legs. And the way that I've always done that is by making the little leg, this like little L, I make that my short leg, and then capital L, I make my long leg. Now, it's always easier, no matter what, to go back to the short leg. So if you know the hypotenuse of the long leg, go back to the short leg and then convert to the other one you're missing, right? Because all of these formulas are going to be in reference to the small leg. So in other words, our short leg is just L, right? It's whatever L is. Our hypotenuse is going to be 2 times L, right? And then our long leg is going to be L times the square root of 3. All right, so these are the relationships. The one across from the 30-degree angle is going to be our little angle, our little leg, because the angle is shorter, so it creates a smaller side. And then the 60-degree is going to create a longer leg. Ultimately, the 90-degree will create the longest leg, which is just called the hypotenuse. All right, it's kind of a very brief summary. If you have any questions on that, please come see me. But this is, in general, how this works. So now we're going to find sine and cosine of both these essentially 30 and 60-degree angles. Okay, so I drew a picture for you as best I could here. The circle looks a little wonky, but you get the idea. This is the first quadrant of the circle. So here we have a reference angle of pi over 6, which is just the whole angle in this case because it's in the first quadrant. So we have pi over 6, which is 30 degrees. All right, we know that the hypotenuse is 1, right? Because we're working off of the unit circle for now. So if this has a hypotenuse of 1, okay, now I can use that to kind of solve problems. So let's just do pi over 6 first, okay? So first we know that, and this is kind of important too, right? We know y is the short leg, because if this is pi over 6 here, this angle, which is the 30 degrees, the short leg is always across from 30 degrees, right? So in this case, y is our short leg and x is our long leg. Okay, so let's find the short leg. So if we know our hypotenuse equals 2 times our leg, we know that 1 is our hypotenuse, so 1 equals 2L, which means we're then going to have to divide by 2, right? So y is going to be 1/2, right? We took the short leg is half the size of it, so if this is 1, this should be 1/2, right? So our sine of pi over 6 is going to be 1/2, and then if we take that 1/2, right? So let's take the 1/2 that we just got for the short leg, plug it in times the square root of 3, right? We're going to get essentially 1/2 times the square root of 3, right? So if you look down here, we kind of did that, right? So over here, we did the long leg. So the long leg equals the short leg times the square root of 3. We know the short leg equals 1/2, right? So the long leg is going to equal 1/2 times the square root of 3, which equals the square root of 3 over 2. So our cosine value, or our x value, is the square root of 3 over 2. So in this case, for pi over 6, you'll notice that sine is 1/2, cosine is 3 root over 2. All right, so now let's do the other one. Let's do 60 degrees. And you'll notice that in this case, the long leg and the short leg are going to flip, right? Because our long leg is now across from the 60 degree, right? Which is this y value. So before our y value was across from 30 degrees, now our y value is across from 60 degrees. So we have the 60 degree angle here. We have the 30 degree angle here, which is our x value. So we're going to probably solve for x first in this case, because remember, we always want to solve for our short leg first, because that'll make our life a lot easier. So let's go and do it. So at pi over 3, 60 degrees, remember that our x is our small leg, and our hypotenuse is 2 times the length of our small leg. So we are going to take 1 equals 2 times our leg, and we're going to get x equals 1/2. All right. So just like before, right, cosine in this case of pi over 3 is going to equal this, right? But let's do y real quick before we get ahead of ourselves. So remember, y is our long leg, right? Our long leg equals the small leg times the square root of 3. We already determined that the long leg was 1/2, right? So in this case, y is the square root of 3 over 2, which means that if we look at this, these are the same numbers as before, right? The only difference is that our x and y values are flipped. And that should make sense, right? Because in this case, if we have the same hypotenuse, in the first case here with 30 degrees, our x value is actually associated with the 60-degree angle, and our y value is associated with 30 degrees, right? And just like on an isosceles triangle, right? If you're across from a 30-degree angle and the angle measures are the same, then the side length, the length of the leg is going to be the same, right? So in other words, to sum this up, the cosine of pi over 3 equals the sine of pi over 6, and the sine of pi over 3 equals the cosine of pi over 6. It's kind of a neat little thing there. But you'll notice a lot of these, if you, like I said, if you reference the unit circle that I gave you in the last lesson, you'll see a lot of these are true. And you'll see that if you're in any other, you can be in any other quadrant, all it's going to do is affect the positive and negative of these. All right, so let's start talking about using reference angles, right? So I've vaguely touched on this a little bit, but we can kind of get a little bit more detail. So find sine, cosine, and tangent of 5 pi over 4. All right, so first of all, we need to know the reference angle, okay? And to find the reference angle, remember that we're going to be referencing the x-axis, right? We need to know what quadrant it's in. That's important, right? Well, 5 pi over 4 is a little bit more than 1 pi, right? Because 4 pi over 4 would be, that's actually a good way of looking at it, right? This is 4 pi over 4 plus 1 pi over 4, right? Which is super important because that'll tell us exactly what our reference angle is. So first of all, you need to find what it's closest to in terms of 0 degrees, which is 0 pi over 4, 180 degrees, which is 4 pi over 4, or 1 pi, right? I just did this to make it a little bit easier for you. And 2 pi, which would be all the way around, right? And that's 8 pi over 4, or 2 pi is the same thing. So 5 pi over 4 is definitely closest to 4 pi over 4, right? Which is pi. So we're going to be on the negative x-axis, right? And in this case, it's 5 pi over 4 minus 4 pi over 4. That gives us our reference angle, right? Because remember, it's our angle minus the reference angle, or plus the reference angle, right? But in this case, like this one was bigger, so we subtracted, and it gives us pi over 4. Now, because we added pi over 4 to our reference angle, or our reference axis, if you want to call it that, right? Because we added pi over 4, we're going to be going pi over 4 down into, right, just to kind of go back over here, we're going to be talking about this gold color, right? Because we had pi and we added a little bit, right? So if we add a little bit, that puts us into quadrant 3. So we added pi over 4, and remember pi over 4 is 45 degrees, right? So we added 45 degrees to our 180 degrees. And if it helps you to convert it into a degree measure and just to look at it, I would get in the habit of learning how to deal with these fractions and how they look on the coordinate plane here. But if for now it helps you just to think of it as a degree measure, maybe you could do that too. So determine the quadrant. We already did this, right? It's in quadrant 3 because we added a little bit to pi. And when you add a little bit to pi, that puts you in that gold quadrant that we were talking about, quadrant 3. All right, so now that we know that it's 45 degrees essentially, or pi over 4, we can just use our reference angles to understand that, okay, pi over 4 is pi over 4. It doesn't matter, right? If we go back over here, all of these thetas, these are all just pi over 4. It just matters if we're adding it or subtracting it according to the x-axis, and that'll tell us if the values are positive or negative for cosine and sine, right? So in quadrant 3, right, which is the one we're talking about, everything is negative, right? And we also know that pi over 4, all of our legs are the square root of 2 over 2, right? So all we're going to do is we're going to take the answers we got from before when we did this problem, right? Square root of 2 over 2 for both x and y, and we're going to essentially just make them negative. That's all we have to do. That's the value of reference angles. If you understand the reference angle and you understand the original angle, all you have to do is assign positive and negative values to whatever the sine or cosine or tangent or whatever you're looking for, right? So if we substitute reference angle values, right, we can assign the correct positive and negatives based on the quadrant. Like I said, in this case, they're both negative. So the sine of pi over 4, remember that was, it was square root of 2 over 2, right? But now it's going to be negative square root of 2 over 2 because we're in this quadrant. Cosine of pi over 4, right? This should actually technically be 5 pi over 4 would be more accurate here because these are in the quadrant that we're looking for. So I'm going to add these 5s, right? Pi over 4 would just be, these would both just be positive because we'd be in the first quadrant. All right, so yeah, so sine of 5 pi over 4 is going to be the negative here, and then the cosine of 5 pi over 4 is also going to be negative, right? Because our originals were positive, and in the third quadrant, we add negatives to them. And then, of course, tangent is going to be, because these are the same, they're just going to be the same thing stacked on top of each other, which is going to equal 1, right? If you want to look through this, it makes sense, right? Sine of pi over 4, and of course, this should be, again, I was using the reference angle, but this should be, if you want to be technical, these should be 5s. There we go. Okay. So, yeah, so this is just tangent just 1. And you'll notice that in 45, 45, 90 triangles, you're going to get a lot of 1s for tangent because a lot of the things are the same. All right. So reciprocal trig identities. So now we're jumping into like the second half here. And we're going to be talking about things that maybe you've heard of before, maybe you haven't. But it's essentially every function, sine, cosine, and tangent, they have multiplicative inverses. And of course, the multiplicative inverse is just going to put whatever it is that we're talking about into the denominator. So in this case, we have cosecant, which is the trig identity, the reciprocal identity to sine. So cosecant, CSC is how we abbreviate it, is 1 over sine. Secant is 1 over cosine, and cotangent is 1 over tangent. All right, which is of course cosine over sine, right? All right, because we flip them. All right, so what we're going to do for a quick trial problem is we're going to find the cosecant, secant, and cotangent of pi over 6. Now remember, pi over 6 is 30 degrees, right? Because this is 180 divided by 6, which is 30. So the cosecant of pi over 6 is going to equal 1 over the sine of pi over 6, right? If we look back here, remember the sine of pi over 6 was 1/2, right? Yeah. Yeah, sine of pi over 6 was 1/2. So we know that we can put this 1 over 1/2. 1 over 1/2 is just going to give us 2. So the cosecant of pi over 6 is 2. And if you think about it, these are just multiplicative inverses, right? If we already knew it was 1/2, well, if we flipped 1/2, right, you'd get 2. All right. So the secant, which is, of course, our cosine, right? Secant is pi over 6. The secant of pi over 6 equals 1 over the cosine of pi over 6, right? The cosine of pi over 6 was the square root of 3 over 2. So we can just flip those, right? This would be 2 over the square root of 3, right? And of course, we can't have the square root of 3 in the denominator, so I rationalized here, right? So I did this. This step may be confusing to people, which I can understand. But essentially, if we just take this bottom fraction and flip it, we're going to get a 2 on top, a square root of 3 on the bottom, right? And you can't have a square root of 3 on the bottom, so I rationalized. Square root of 3 over 3. Okay, so the cotangent, right? And this is this math would get a little bit confusing, so I did a little bit of that here for you. The cotangent of pi over 6 is the cosine of pi over 6 over the sine of pi over 6. And of course, that equals the square root of 3 over 2 divided by 1/2. And when we divide by a fraction, we KFC, right? So keep, change, flip. And we have the square root of 3 over 2 times 2 over 1. Of course, the 2's cancel out, and you get the square root of 3. So the cotangent of pi over 6, or 30 degrees, is pi over 3. All right. So that was just kind of a quick introduction to what these things are. And then we went into a problem just kind of talking about stuff we've already talked about. But yes, remember cosecant. I know cosine and cosecant sound like they should go together, but they don't, right? Cosecant is with sine, secant is with cosine, and then cotangent's with tangent, which, you know what I mean? That one actually makes sense the way it should probably. But there's, yeah, anyway. So, last thing we're going to talk about is the Pythagorean identity, right? And what this, and maybe some of you have even noticed, like, we could use the Pythagorean theorem to solve for some of these sides, right? And that is true, right? Especially if we know the actual concrete value of one of them, we can use that to solve for one of the other sides, assuming that we have the same angle measures or we're in the unit circle. But what we can do more specifically is establish a set of identities. So our question for this is going to be, what are the sine theta and and tangent theta if cosine theta is -3/5 and the terminal side is in quadrant 3? Okay, so anytime you hear the term terminal side in quadrant 3, your brain should be popping off with, okay, negatives, right? We're just basically going to solve it in the positive quadrant and then add negatives at the end. It's kind of what you do, right? Or at least you're going to be able to reference it and know that it has to be a negative angle, right? Or not a negative angle, but the values are going to be negatives. All right, so that's not how you spell Pythagorean theorem. Okay, but anyway, that's what this is supposed to say. Pythagorean theorem is, of course, in this case, right, it's a squared plus b squared equals c squared normally, right? But in this case, it's going to be our y squared. It's going to be our y squared plus our x squared equals our c squared, which in this case is 1, right? There we go, I fixed it. Okay. So y squared plus x squared equals 1 squared, right? That's just based on this being the right part of the triangle here. Which means that, remember that our y value is our sine and our x value is our cosine. So we can rewrite this as sine theta squared plus cosine theta squared. And the reason why, and we write this like this, right? If we look in this little gold box. So we put the sine here next to the theta because we don't want people thinking that this is just, that the theta is squared, right? Because that's often what happens. If this didn't say sine theta, this said like 32 degrees or something like that, you'd think the 32 degrees would be squared, right? And it's really it's the whole function, right? So it's sine squared theta. It's essentially this, right? If you look down here, sine squared theta is sine theta times sine theta, right? It's not sine of theta squared. Okay, it's the function twice, just to be clear. I just want to make sure that that's understood. So when you see it, if you see the little squared before the theta, it's basically saying you have to take sine of whatever that angle is. So let's say it's 30 degrees. That would be sine of 30 degrees times sine of 30 degrees. It's not sine of 900 degrees, right? Okay. All right, so let's do this. So remember, we are trying to find sine theta and tangent theta if cosine theta is this, right? Now, what's cool is, remember, based on this formula, right, we already know the hypotenuse is 1. We know that cosine, which is our x value, is -3/5. We have everything we need. We only have one variable left, right? So we can solve for that. So what this will turn into is sine squared theta plus -3/5 squared equals 1. We can simplify the -3/5 by kind of distributing this exponent, right? So sine squared theta plus 9/25, right? Just squared both of these numbers, equals 1. All right, so what I did is I subtracted 1, or I subtracted 9/25 from both sides, right? So if you're wondering how I got down here, right? I subtracted 9/25 from both sides. Subtracting 9/25 will give you 16/25, right? So sine squared theta equals 16/25. So in order to get rid of, this is sine squared of times sine theta, right? So we can take the square root to just get sine theta. So sine theta equals plus or minus the square root of 16/25. And then, of course, sine theta is going to equal plus or minus 4/5 because we can take the square root of 16 and the square root of 25, and it'll give us 4/5. Now, sine of theta equals plus or minus 4/5, right? Well, which quadrant are we in? We're in quadrant 3. So can sine theta, can this angle measure equal something that's positive? And the answer is no. It's going to be negative, right? So we know that it's the negative value here because it tells us we're in quadrant 3. So yeah, in quadrant 3, sine theta must be negative. So sine theta equals -4/5, right? And now to find the tangent, well, we know the cosine, right, is -3/5, and now we know the sine is -4/5. So to find tangent, we're just going to have to do this really silly looking fraction here, right? So we're going to have sine theta, which is negative 4 over 5, and we're going to have cosine theta, which is negative 3 over 5. You'll notice that the negatives and the denominators will cancel, which will give us 4/3. So tangent of theta is 4/3, which means cotangent of theta is 3/4, right? Just as a fun little side fact. All right. That's it. So we learned quite a bit today. Really used reference angles a lot and different things. So first thing we did was relate trig functions to reference angles right here. And then we use special right triangles to evaluate trig functions. And then we used reciprocal trigonometric identities and the Pythagorean theorem to evaluate trig functions. So that's where we talked about these. All right. Well, that's really it. Please, if you want to really buckle down and practice something, go to your unit circle that we talked about and look at it and see if you can figure out where those numbers came from, and then why, and then look at the reference angles and look how they relate to each of the different values within the different quadrants. It's actually kind of interesting, but that's it. I will see you in the next video.